Good morning, good evening, good afternoon. Welcome to the next MECI Alliance seminar talk. My job today is actually just to introduce our host for today. So one of the world's leaders in control systems. I'll introduce our own Dr. Anaswamy to introduce our speaker. Dr. Anaswamy, take it away, please.
Well, thank you so much, Brian. That's very kind of you. It is a pleasure for me to welcome one of our own, Neera Jain. She got her undergraduate degree from our department in 2006 and went on to do her master's and PhD in University of Illinois. Urbana-Champaign is now a faculty member, assistant professor in the School of Mechanical Engineering at Purdue. She directs the Jain Research Laboratory, and her goal is to advance technologies that have a lasting impact on society through a systems-based approach. It's grounded in dynamic modeling and control theory. A major thrust of her research is the design of human-aware automation through control-oriented modeling of human cognition. She also works in the space of optimal design and control of complex energy systems. Her research has been focused and featured in NPR and Axios, and she's a contributor to Forbes.com as well, where she writes on the topic of human interaction with automation and its importance in society. Her research has been supported by the NSF, Air Force Research Lab, ONR, Naval Research, and private industry. I'm sure you're all looking forward eagerly to her talk as I, so take it away, Neera. About 40 minutes, and then we'll open it up for Q&A.
Sounds good. Thank you, Dr. Anaswamy, for that introduction. Super. I'm very excited to be back virtually at MIT and happy to share my research with everybody today. I'm going to go ahead and share my presentation here. Actually, let's go into, oops. Do this. And get my pointer in here. Okay. So the title of my talk today is Enabling Human-Aware Automation, a Dynamical Systems Perspective on Human Cognition. And before I jump into the topic at hand, I did want to take 2 slides actually, just to talk a little bit about that other half of my lab that Dr. Anaswamy mentioned. So in addition to working on control in human-machine interactions, I also do quite a bit of research in the space of optimal control dynamic modeling for different types of energy systems with an emphasis on thermal energy systems. So I wanted to highlight some of this in case it's of interest to any of the attendees, and I'm happy to take conversations offline on any of that. So one of the things that we've been focused on for a couple of years now is control co-design for transient thermal management. And this is something that's motivated by broadly increased electrification across a lot of sectors, but in particular in the aerospace sector, where current commercial and military aircraft are actually approaching 1 megawatt of installed electric power. So these are massive amounts of power, and as soon as we have lots of electronics, we have a lot of heat. And not only are these heat loads larger in magnitude, but they're also more frequent and more transient. And so there's really an opportunity here to think about, and a need to think about, how do we use real-time control to actually mitigate the negative effects of these increased heat loads. And one of the approaches that we've taken is control co-design, which involves thinking about how do you design your plant and your controller together, because we found that in order to actually be able to meet our ultimate control objectives, we actually need to redesign the physical system as well. And one of the challenges that arises for these types of systems is the fact that the modeling fidelity that you need to synthesize a controller, for example, is very different than the modeling fidelity that you need to potentially design, for example, a heat exchanger or a pump, particularly because of the way that we model a lot of thermofluidic components with nonlinear, semi-empirical relationships and so forth. And so what we have developed, my former PhD student, Dr. Austin Nash, who's now a professor at Kettering University, is what we're calling a model fidelity-based decomposition hierarchical control co-design framework. A little bit of a mouthful, but essentially an algorithm and framework for additional algorithms that leverages not only the need for different modeling fidelity at different levels of a more complex energy system hierarchy, but gives you the ability to, again, consider both plant parameters and control parameters together. And so this is work that we recently published both in Transactions on Control Systems Technology and the Journal of Mechanical Design. And we're in the process of validating the work on an experimental test bed. Another area, a big focus of research for us, is on dynamic modeling and control of thermal energy storage systems. So we've been invested in first modeling and now more so control of different types of thermal energy storage, whether that be sensible thermal energy storage in the form of stratified hot water tanks, which have been around for a long time, but actually have extremely complicated dynamics, as we've shown with some switched modeling frameworks for them. We've also done and have ongoing work in understanding how to model phase change material-based heat exchangers and actually integrating them into the larger complex systems that I described on the first slide. And also, we've done some work on ice storage, so another two-phase storage mechanism for residential HVAC systems. And again, thinking about how do we optimize the charging and discharging characteristics and decisions for these kinds of systems to, for example, optimize economic cost for a user. So this is just a little bit of a splash on that work, but I'm going to go ahead and turn back to the main topic of today's talk, which is really about how humans interact and trust automation. So one of the things that I think probably everyone has noticed and can agree with is that our interactions as humans with automation are increasing. But what's really important and what motivates our work is the fact that the outcomes of these interactions are still falling short of our intentions as, you know, maybe the engineers who designed the technology and the expectations of the users who are trying to use that technology. And the figure here that I'm showing, or this image, is from a hospital in Italy. This was posted early on in the pandemic. I can't believe it's been almost a year. And in this hospital, a series of nurse robots were deployed. And the ICU director was quoted as saying, "You have to explain to the patient the aim and function of the robot, because the first reaction is not positive, especially for old patients." And you can imagine that the patient is not only obviously sick, they're probably scared, they're in an uncomfortable environment, and perhaps all they want to see, or would reassure them, is to see a human nurse, for example, or human doctor. And so they really may not be thrilled to have a robot roll into their room and try to interact with them. And of course, though, from an engineering and a technology standpoint, the purpose of these robots is to help alleviate the workload of nurses and doctors so that they can attend to more critical patients, or perhaps even to help them maintain more distance from patients sick with COVID. And so this is just one of many examples of why we really have a lot of work to do in thinking about how can we improve these interactions of humans with automation. So we know that there are several cognitive factors that do in fact affect how humans interact with automation, how they perceive that interaction. And in fact, there are several conceptual frameworks that capture the complex interactions between what these cognitive factors that I'm referring to, thanks in large part to the human factors community and the cognitive psychology communities that have done a lot of work over the last several decades on this. This is one example of such a sort of conceptual framework, and I've highlighted a couple of words in yellow that I'm going to be using throughout today's talk. And so, for example, we can see that the reliance of the human on the automation, their ultimate decision to rely or not rely on automation, is affected in large part by their trust in that automation, which in turn is affected by the accuracy of that machine or that autonomous system. And as you can see yourself, there are several other factors that can play into this. Now, of course, as engineers and specifically controls engineers, this is extremely useful, but I really need a quantitative mapping of this type of information. And indeed, quantitative models have been developed that predict things like changes in trust or workload, both of which have been shown to be dynamic quantities. But there are two critical gaps that motivate the work that I'm specifically going to talk about today. The first of those is that we don't just need a quantitative model of these interactions, but we specifically need a model that maps automation outputs that we can control to the cognitive factors that ultimately affect the human's decision-making. And then once I have such a model, I want to be able to design control policies that actually enable the automation to adapt to that human's cognitive state. So what I'm going to talk about today is how we've addressed both of these. So to outline the talk, I'm going to first define automation transparency, which is going to be the control variable that we're going to be using to affect the human's interactions with automation. I'll describe the POMDP model of human trust and workload that we've developed to capture these interactions and these dynamics. I'll then talk about the human subjects experiment design that we designed and implemented in order to collect data to train that POMDP, and then go into the closed loop policy design and its validation, and wrap up with some conclusions and some related and ongoing work. Oops. So automation transparency is a quantity that affects critical human cognitive states, namely trust and workload, which is what we're going to be focused on today. And we use specifically a definition of transparency based on situation awareness-based agent transparency that was developed by Chen. And I've written it out here, and the key issue, or the key definition here, is that transparency affords or is the descriptive quality of an interface to afford an operator's comprehension about an intelligent agent's intent, performance, future plans, and a reasoning process. And so these bolded words are really the critical ones. And I think it's helpful to define this in more detail in the context of levels of automation. And when I say levels of automation here, I'm not referring to the SAE levels of automation that you might be familiar with respect to self-driving cars, but a more fundamental definition of levels of automation that was first developed by Parr Surman. So at the lowest level, the simplest type of automation we can have is acquisition automation, where its goal or its objective is to acquire information, raw information for the human. Next level of automation would be analysis automation, where the automation is able to process or analyze that information and share that with the human. The third level of automation is decision automation, where based on that analysis, a decision or recommendation is made by the automation to the human. And then the last level of automation, which I've not pictured here, would be action automation, where the automation actually has a control authority to act on that decision or recommendation. And an example to kind of anchor yourselves on decision automation would be something like Google Maps, which can give you turn-by-turn directions, but doesn't actually drive your vehicle. So it's up to you to choose whether or not to comply with those directions that you're being provided with by Google Maps. So we can think about transparency in sort of a reverse direction, if you will. So the lowest level of transparency would be that in which only the decision or the recommendation is communicated to the human. A medium level of transparency would be one in which both the decision is communicated, but also some of the analysis or process information that went into making that decision. And then the highest level of transparency is one in which the automation does both the sharing of the recommendation and some of that sort of analysis, but also provides the raw information to the human so that they can also actually fully understand that recommendation. So transparency is particularly important for us because we know from the literature that it affects two of these cognitive states that we're very interested in. So we know that increases in transparency typically lead to increases in trust, which we can measure or observe through increases in the human's compliance. We also know that increases in transparency often lead to increases in workload, which we can observe typically through increases in their response time between when they receive their recommendation and when they respond with their decision of whether to comply or not comply. And so from the perspective of us wanting to develop a quantitative model of this relationship, we need to observe, or it's important to sort of take note of the following. So first, the only things that we can actually directly observe are compliance and response time. Trust and workload are dynamic states, but they are, for all intent and purposes, hidden. There are some ways in which we could potentially measure those quantities. Oftentimes in human subject experiments, we ask humans to self-report this information, but from a feedback control perspective, constantly querying the human would also typically not really make sense. So for our perspective, we treat these as hidden states that at best can be inferred or estimated through these observations. It's also important to note that not just transparency affects the state evolution of trust and workload, but also other factors like the system's reliability, the context of the situation, et cetera, can also affect that state evolution. So we've got these inputs that affect our states, these outputs that we can measure, and through which we could potentially infer or estimate our states. And so a natural choice for a modeling framework that we're using here is a partially observable Markov decision process, or a POMDP. And a POMDP is a 7-tuple that consists of states, actions, observations, a transition probability function that governs the state evolution of the dynamics, and then a mission probability function, which tells us, for example, the likelihood of making an observation O, given that the process is in some state S. And it also has the ability to be used for optimal control. So there's a reward function that we can design and pose and then solve in order to back out an optimal sequence of actions to drive the system to, or the process to, a certain state of interest to maximize a reward. And this structure is really in many ways analogous to a state space model, albeit probabilistic. So we can use this POMDP framework to consider modeling human cognitive dynamics, and we do that as follows. We define our states to be trust and workload, and each of those can take on either a high or low value. We define our observations to be compliance and response time. And then we've defined our actions to be certainly transparency, which again is a controllable input or action in this case. And then 2 additional actions, which, as I mentioned, affect the state evolution, although in this case, we can't directly control. One of them is the recommendation that's actually made by the decision aid or the automation. And then the other one is the experience that the human has of that automation, which we define as either being faulty or reliable. So in other words, was this particular automation faulty or reliable at the last trial or interaction that the human had with it? And I want to point out that this choice of sort of definition for the action, states, and observations at this stage is still fairly generic and applicable to pretty much any type of intelligent decision aid, or that third type of level of automation, which I described earlier. So today I'm not going to be talking about action automation. I'll stop at decision automation, but I did want to mention that we have in fact extended this framework to action automation as well. An example of a type of decision aid that could fit into this context would be something like a health recommender system, where the stimulus is either the presence or absence of a disease. And the example that I'm going to talk about today is a reconnaissance mission scenario where the stimulus is either the presence or absence of danger. So one of the assumptions that we make for this model that I'm talking about today is that trust and workload are conditionally independent. Doing this decreases the number of parameters that we have to estimate, which simplifies the model considerably, and changes our transition and emission probability functions to be as follows. So in other words, we can actually identify or train our trust model separately from our workload model. I want to mention that in recent work, we have actually relaxed these assumptions and trained fully coupled models of trust and workload, and found that we actually, that they did not really outperform the independent models. So the coupling between them is sort of sufficiently weak, at least in this context. And I'm happy to talk about that afterwards if there are questions. In terms of defining the different variables, our states, actions, and compliance are all defined as discrete random variables. You might have noticed on the previous slide that response time was actually defined as a continuous random variable. And so I wanted to share just quickly why we do that. So if we plot response time, even just based on the data that we collected through our study, which I'll describe later, human response time kind of takes on this type of distribution, which you can see looks like a Gaussian distribution and an exponential distribution combined. And we actually call that an exponentially modified Gaussian distribution, and it's given by this expression. And interestingly, it's been used by the psychology community to model response time, human response time, since the 60s. There's lots of literature since then, but I wanted to include this, one of the first articles, just to kind of highlight how kind of well established this relationship is. And it was pretty interesting for us to see that our data very much lined up with this type of distribution. So that's why we made a choice to actually model this particular variable in a continuous fashion. And just to show that there is a flexibility in the POMDP to actually mix these discrete and continuous variables, which is very useful. So having defined our POMDP, we still need to actually identify the parameters of our transition probability function and emission probability function, which ultimately characterize the dynamics of the system. And so to do that, we need human data, and we collected that through the implementation of a reconnaissance mission study. Our study was adapted from one that was published back in 2015, and we've made some modifications and redesigned the transparencies for our work. So the objective for each participant in this study is to surveil several buildings in minimal time. So each participant was asked to surveil a building. Before they would do so, they had to make a decision as to whether or not to wear light armor or heavy armor before going in to check to see whether or not there was or wasn't danger in that building. And it would take more time for them to put the heavier armor that would protect them more. And so we built into the experiment a trade-off between fast surveillance and personal safety. The human in surveilling these buildings was assisted by a virtual robot, which acted as an intelligent decision aid. And we did not tell the humans this, but the robot was only 70% reliable. So there were going to be situations in which the robot would make the wrong recommendation about which armor to wear before the human would go in to surveil the building. And each participant completed 3 missions with 15 buildings each. And in each mission, they interacted with a virtual robot that used a different level of transparency when communicating the recommendation to them. So let me walk through one trial just to make sure everyone's on the same page about what was happening in this experiment. So, and again, this was all done on a computer. We collected all our data through Amazon Mechanical Turk. So the participant would be told that the robot had gone in to search a building, and the robot would return and either report that there was no danger or that there were gunmen present and make a recommendation as to whether the human should wear light armor or heavy armor before going in themselves to surveil that building. At this point, the human had to make a decision of compliance or non-compliance. Let's say they were given a recommendation of light armor and they chose to comply. They would put on their light armor. It would take them about 3 seconds to do so. And if they went in and there was no danger, no problem, they move on to the next building. If they went in and the robot had been wrong and there actually were gunmen present, the human would get injured and they were penalized with a 20-second wait time. And in fact, in the experiment, we did make them wait for 20 seconds before they could go on to the next building. Now, had they not complied and worn heavy armor instead, it would take them 7 seconds to put on the armor. But now whether there wasn't danger or there would be no additional time penalty for surveilling that building. So I mentioned that there were 3 different transparencies with which they might receive data depending on which robot they were interacting with. In the lowest transparency case, this was what the participants would see. They were given a status bar as a robot was surveilling the building, and then finally a report and a recommendation, and that was it. In the medium transparency case, they had that information, but also this kind of sensor reading that had a threshold. And so they could see how far above or below that danger potential threshold the robot was sort of reporting that recommendation with. And then in the highest transparency case, all of the information from the other transparency levels was there, in addition to 7 thermal images that the robot had collected while inside that building. And so this gave the human the ability to actually scan those thermal images themselves and, for example, look for human forms to decide for themselves whether or not they thought that there might be gunmen inside the building. And so you can see how there's increasing amounts of kind of clarity and information being communicated to the human with increasing levels of transparency, but how you could also expect that the workload of the human is also increasing as they're being provided with more information. So we collected data from about 200 participants, and we aggregated that data to train a single POM-DP model to represent all of the participants. And I'm not going to go through all of these diagrams, but I just will pick a couple just to give you some intuition for how the behavior of the humans translated to the probabilities in these transition and emission probability functions. So in our trust model, if we look at the emission probability function, we see that if the human is in a state of high trust, they were very likely to comply. And likewise, if they were in a state of low trust, they were very likely to not comply or disagree with the recommendation. Interestingly and importantly, there still are non-zero probabilities that they, for example, might be in a state of high trust, but still choose to not comply or disagree with that recommendation from the decision aid. If we look at the transition or one of the transition probability functions, these are conditioned on the different actions. This particular probability transition function is for the case when the recommendation is to wear light armor and the robot made a reliable recommendation at the last trial. In green, we show then the low transparency, medium transparency, and high transparency, and how each of those transparencies affects that transition of the human from a state of low trust to high trust or vice versa. And what we see is that it's the highest transparency here in maroon or red of transitioning the human from a state of low trust to a state of high trust. Likewise, and interestingly, it was also the highest transparency that had the highest likelihood of driving a human from a state of high trust back down to a state of low trust. And so what this actually means is that higher transparency is better for trust calibration. So remember that our goal is not just to maximize the human's trust, it's really to help the human distinguish between when they ought to trust and when they should not trust the automation. And so in other words, we have the most control authority with that highest transparency. In the workload model, we can see, again, our emission probability function shows us what we expected, that when the human is in a state of low workload, a very high likelihood of fast or short response times. When they are in a state of higher workload, our distribution of response times is much larger and covers a larger and longer range of response times. And then if we look at the same transition probability function for the workload model, again, light armor recommendation, last trial was a reliable one. We see that it's the highest transparency that has the highest likelihood of driving a human from a state of low workload to high workload, which makes sense. And also, if the human is already in a state of high workload, showing them high transparency, again, has a very high likelihood of keeping them there. So in the interest of time, I won't go through any more of these, but hopefully you're getting a sense for how the model is in fact capturing this important probabilistic behavior on the part of the human. And so given that we have that model, we now have the ability to actually pose and solve an optimal control problem to actually come up with a policy for adapting the automation transparency to the human in real time. And so using our POMDP framework, we can do this specifically by defining this reward function. So for this context, and in this sort of human-machine interaction scenario in a reconnaissance mission, we felt that the control objective really is to minimize mission time. And there are two ways in which the human can accomplish this for this scenario. The first is for them to reduce the number of incorrect decisions that they make, certainly mainly so they can avoid that 20-second penalty. And that really is related to them calibrating their trust appropriately. And then they can also decrease their mission time by reducing their response time, which is really related to reducing their workload. And so what we decided to do is to define two reward functions, one to address each of these mechanisms for minimizing mission time, and then basically have a weighted reward function that trades off between the two. So the decision reward is maximized when trust is calibrated. So remember, I told you that the robot is not always correct. And in fact, it had a 70% reliability rate. So 70% likelihood of a true negative or true positive, 30% for the false positive or false negative. And so what we did to define our decision reward was to actually define it in terms of the human's choice and the true situation. So in other words, if the human chooses light armor and the gunmen are absent, then it takes them 3 seconds to surveil that building. But had there been gunmen present, as I mentioned before, it would actually take them a total of 23 seconds to surveil that building and so forth. So what we did was to say that we will define the penalties in our decision reward to be actually equivalent to the amount of time and seconds that they actually have to expend in each of these different situations, where with this being the situation that we really want to avoid or help them to avoid. Similarly, the response time reward is maximized when workload is reduced. And so we simply defined our response time reward to penalize these longer response times, and we just defined it as the opposite of their actual response time. I also wanted to mention the details of this are in our manuscript that I'll mention later, but both of these reward functions, as I defined them here, were defined in terms of observations, but actual reward functions do need to be defined in terms of states and actions. And so we transformed each of these reward functions into the standard form in order to actually solve the POMDP. So as I mentioned, we define a total reward, which is a weighted sum of these two rewards. And we've got this weighting factor zeta that allows us to trade off between the two. And we can solving the POMDP, we used a QMDP method, which essentially gives us sort of an infinite time solution for the optimal control problem and tells us the optimal transparency is a function of the state that will maximize our total steady state rewards. And we can use this discounting factor gamma in order to basically give more importance to near-term rewards because we're not actually interested in that infinite time solution. So we put more weight on basically 15 trials, which was the length of a mission. So what I'm going to do now is to walk through the different control policies, a couple different control policies, and then show some of our validation results. So we solved this control policy solved the POMDP for 3 different values of zeta to understand how that trade-off affected the basically optimal policy. So if we start with a zeta of 0.95, we're essentially giving very high importance to the decision reward as compared to the response time reward. And I want to focus on these top 2 figures right here, where the recommendation is light armor, and either the robot was faulty at the last trial or reliable at the last trial, where the last trial would be the previous building that was surveilled. And on the x-axis here, what I'm showing is the likelihood that the human is in a state of high trust. On the y-axis for each of these quadrants is the likelihood that the human is in a state of high workload. And so what this is showing us, again, the color scheme is the same as was for the earlier diagrams, low, medium, and high transparency, is that if the human is very likely in a state of high trust, and the recommendation that was just made by the robot was to wear light armor, the optimal thing to do in this situation is to actually show them the highest level of transparency. And that is because if the human is very likely to be in a state of high trust, then they're very likely to comply. But if they comply with a light armor recommendation and the robot was wrong, then they incur that largest penalty because where they wear light armor, but they actually get injured because there in fact was danger in the building. So this is sort of the riskiest situation for the human in terms of them making incorrect decisions. When we first saw this in our research, we actually were a little bit surprised because typically you don't use high transparency when the human is already very trusting or in a state of high trust. But when we analyzed it further, it actually made perfect sense that in this situation, the controller is actually trying to mitigate overtrust. It's saying, hold on, you are so likely to trust me right now that I want to give you extra information so that you can be sure that I'm giving you the right recommendation. And it's worth it for you to take the hit on response time in order to really analyze that extra raw information that I'm going to provide to you. So this was super exciting for us to see that the controller actually was able to discern this particular case of a risk of overtrust. If we back off zeta to be 0.91, we're looking at the same kind of a similar diagram. What we see is a similar breakdown, but basically because even though we're still really heavily weighting the decision rewards, backing off on the zeta and putting a little bit more emphasis on the response time rewards means that the optimal thing to do is to only show the highest transparency when the human is really, really likely to be in a state of high trust, and otherwise try to use medium transparency to help mitigate overtrust. And if we back off zeta to be 0.5, so we're giving equal weighting to the response time rewards and the decision rewards, the optimal thing to do is to actually never use high transparency. Instead, medium transparency is used heavily. And the reason here was that, as I'll show later, the highest transparency caused such an increase in the workload of the human that if you really want to minimize the response time, it doesn't make sense to use the highest transparency. So this is really neat to see what the optimal control policy says we ought to do, but we went ahead and actually ran an additional set of human subject studies, implemented these different control policies to actually validate them. So again, we conducted 2 different studies. It was a between subject study where for one study with about 100 participants, they saw 2 of the control policies and a fixed high transparency, so kind of like an open loop scenario. And a second study where those participants saw a fixed high transparency, fixed medium, and then variable transparency based on zeta being 0.91. And again, we randomized the order of missions to avoid ordering effects, and then conducted all of these on Amazon Mechanical Turk. So all of the data is kind of aggregated here, and I'll walk through this chart in kind of steps. So the first thing I'm going to highlight are what I'll call open loop control policies. So this low, medium, and high were situations in which the human was shown the same transparency. So we weren't using the closed loop policy. And what you see plotted on the left are the total decision rewards. On the right are total response time rewards. And as we expect, as we increase the transparency, the total response time rewards goes down, meaning that the human had to use the response time really went up, but their decision rewards were maximized. If you showed the participant the highest transparency every time, they were always able to make the correct decision. If we now look at what happens with our different control policies, we see a similar trade-off that we expected and wanted between response time rewards and the decision rewards. So as we increase zeta, we see that the response time does take a hit. The human used more response time, but in fact, their decision rewards went up and got closer to sort of this high transparency all the time case. And so the takeaway here was that, in fact, we actually, with our closed loop policy and tuning it appropriately, we're actually able to trade off between these two mechanisms to help the human minimize their mission time, which is what we wanted to see. So to summarize, what I presented today was a POMDP modeling framework that we've used to model the probabilistic state evolution for both human trust and human workload. And we used a model-based static control policy to actually capture not just the dynamics and sort of the optimal policy for adapting transparency to an individual participant, but really showed how, for example, high transparency could be used to mitigate the consequences of overtrust. And we were able to validate this through closed loop policy, through closed loop experiments where we actually implemented the policies. So in the last, keeping an eye on time, in the last couple minutes, I wanted to talk about some related work that we've been doing and are continuing to do in this area. Earlier on, and actually we're kind of revisiting this now, we've also looked at the use of psychophysiological data in order to, for example, measure or estimate things like human trust in real time. All of the work that I shared today was only relied on behavioral data collected from humans, but there are lots of different situations in which we can collect psychophysiological behavior and where that could be augmented, for example, with behavioral data to potentially improve these interactions. And so we have an article out where we use a classification model based on the electroencephalogram and galvanic skin response to estimate human trust. We've also, as I mentioned, extended the framework I described today to an action automation scenario in a self-driving car context. And then maybe most related to the work that I just presented, which was mostly published, pretty much everything I described today is from a journal article that we just published in IEEE Control Systems Magazine in December. So feel free to check that out for a lot of detailed information that I wasn't able to cover in the talk. But also in December, we had a paper at the IFAC Cyber Physical and Human Systems Conference, where we took the same data that we collected for the other article, but asked ourselves, can we do better on the modeling side? So I mentioned that we aggregated all of the data from 200 participants to train a single POMDP model that we then used to represent everybody. But realistically, not any two humans are alike, and that was probably a little bit of a stretch to say that that model would be accurate for everybody or equally accurate for everybody. And so in this paper, what we aim to do was to apply clustering methods to that data to think about, okay, are there dominant trust, and we specifically focused on trust here, are there dominant trust behaviors among our population of data? And if there are, could we use maybe just a few different POMDP models to do better in terms of designing these adaptive transparency algorithms? And to make a long story short, what we found is that there really were two dominant groups, which we called followers and preservers. The followers were very compliant. They complied, I think, 90% of the time or close to that with the automation's recommendation. Whereas the preservers, we named this group so because whenever they were provided with a light armor recommendation, remember that was a risky situation, they almost always did not comply and just put heavy armor on anyway. So they were very worried about getting that 20-second penalty. And so we trained two models for these two different groups, or the clustering algorithm actually sort of gave us then the two different POMDP models. And then we solved each POMDP using the exact same reward function that I described today to get two optimal control policies, one tailored to each group of people. And you can compare this figure to this one and this one to this one. And what we're showing is that these are, again, that sort of high risk case where the recommendation is light armor. And for the followers, the optimal thing to do was to show them the highest transparency, almost independent of what their trust was, because they were so likely to comply with any recommendation that whenever the recommendation was light armor, the best thing to do for them would be to just show them the highest transparency so that they would pause and not just comply and actually take a look at that additional information. Whereas with the preservers, because they almost always wore heavy armor, the optimal thing to do was to just show them the lowest transparency, because showing them more information wasn't going to actually change anything and might just increase their workload. So you can see that if we can understand some of these dominant but very different behaviors, it can lead to very different optimal strategies for helping to mitigate that individual's trust. And so we haven't had a chance to actually implement this in closed loop, but that's something that we would certainly like to do. So with that, I'm going to wrap up. I've included a couple of citations to some of our relevant work, but you can certainly go to our website or Google us and find other papers. I want to thank a couple of important people before I wrap up. The first is Professor Tahira Reed-Smith, who's been my collaborator in this area for several years. She is an expert on user-centered design and also brought a lot of the expertise on human subject experimentation and psychophysiological sensing to our collaboration. My former PhD student, Dr. Kumar Akash, who's now a researcher at Honda Research Institute, was the primary grad student who really led all of this work. We had a couple undergrads who contributed to what I presented today. Griffin McMahon, who actually was a lead author on the clustering paper, and who is now a grad student at UPenn in the GRASP lab, and Caitlin Polson, who worked on our reconnaissance mission study a few years ago, and then Dr. Wanlin Hu, a former student of Professor Reed-Smith's, who also worked on our earlier work with trust modeling and psychophysiological sensing and is now at Stanford. So thank you everybody for your attention. I'm very happy to take any questions.
Right, great. Thank you, Neera. That was fantastic. I learned a lot and was really fascinating and an extremely important area of research that I think we have to address as we move the needle, towards more and more autonomy and better understanding of how we can navigate this changing landscape. So I want to ask one quick clarification question, and I see that there is a Q&A. There's a question on the Q&A, and which I'll get to in a minute. And just a quick note to everybody, just type in your questions either in the Q&A or chat, and the Q&A is preferable, and we will get Neera to respond to it. So keep entering your questions. So my clarification question, in the context of the reconnaissance problem, which is really interesting, how did you set up the transparency measure? So what does it mean to say high transparency and medium and low?
Okay. So the transparency is really, so this part is probably this was honestly the most challenging piece for us. Let me see if I can do this faster, my exit. So I showed those 3 different sort of interfaces that we designed, and that was, let me see if this is going to let me escape from, okay, here we go. So the transparency, I guess, measure, if I'm understanding your
yeah,
question,
right, exactly, yeah,
was really the design of these. And I'll be honest, we actually went through 2 iterations of this, because our first stab at designing these, in our first attempt, after collecting the data, we saw that we actually had not designed our medium and high transparency to be distinct enough, and they weren't actually having any sort of different effect on the humans. And this is challenging because there's not really like a clear rule book on how to do this. So there are guidelines for what it means to design different interfaces with different levels of transparency. But this is more of an art than a science in terms of how to do that. So we use the guidelines from the situation awareness-based agent transparency, where again, this is sort of the lowest level is supposed to just report, again, the recommendation, some analysis, more of the raw information. And once we kind of use that as an anchor, that's what guided this design. But yeah, to be very frank, this was probably the most challenging part to figure this out. And then once that was done, with our second iteration, we ended up collecting data and then found that the POMDP actually made a lot of sense. And so then we felt confident that we had done a good job with this design. But there are people who do research just on the transparency piece and just on the interface design. And that's not necessarily our explicit focus.
Exactly what I was looking for. Thank you. So, okay, now I'm going to take questions. So here's one. How would you close the loop and go back to the initial example from the Italian hospital where you have like a third party, the robot and operator, and the patient who has much lower knowledge. So I mean, like for instance, if there is a patient who may not know what to do of any transparency information that you provide.
Sure. So, and I think this gets a little bit more into kind of thinking about the purpose of, let me say this. So in terms of closing the loop, because our control input is the design of that interface, honestly, this is a place where absolutely one would need to be collaborating with folks who are really experts on just how to actually design that interface and what does it mean to communicate information, right? So closing the loop is only as good as your actuator. And in this case, the actuator is that interface design. So I would say that if in order to close the loop, for example, in this situation, we would also necessarily rely on people who are, and maybe this is really human factors experts and cognitive psychologists who are very good at understanding, well, what, and there are guidelines for how to display information, for example, right? So that people understand it. There's a lot of, you can imagine any number of different situations in which we as humans all the time are interacting with displays these days that have been very carefully designed, with the intention of making them easy to use right away without any training, any prior knowledge, et cetera. So if I'm understanding the question correctly, I think that would be, you would need to make sure that you actually had an actuator that was effective. But if you had that, then I think, again, obviously this particular feedback control problem that we've posed relies on having some observations or some estimate or inference of what the human's cognitive states are. And so there's really, actually, maybe I can go back. Oh no, let me go forward. So in order to close the loop, we really need all these pieces, right? We need a model, and the POMDP modeling framework is in part what I described. And we use that for both, our plant model, but also for estimation. And then you also really need the right actuator in that system and the appropriate sensors, which were the behavioral responses. So it's not trivial at all to necessarily translate this to other contexts, but if you do have those building blocks, then this is a framework that we found is repeatable. Like, as I said, we've done it in a driving context where you can actually use this overall framework and approach to then close the loop in the same way.
Thank you. The next question, again, I think we probably take this one as the last one. First, a clarification. So in your, again, reconnaissance problem, remind me what the penalty and reward were, and I have a follow-up question after that.
Sure. So the penalties were really was all defined in terms of the amount of time that the and actually, let me go to the confusion matrix we had here. So for example, we did define two different reward functions, but the more critical one that I focused on was this decision reward, where, again, depending on the human's choice and what the true situation was, they would incur different amounts of time in surveilling a given building. So at the fastest they could ever surveil a building would be 3 seconds. The longest it would ever take them would be 23 seconds. And so that was the penalty that they incurred.
So I guess here's my question: as we sort of take this forward and apply to generic contexts of human automation interaction, these things become so nonlinear and extremely complex. So, for example, it's not just the quantification of these things are really difficult when the penalty between 23 seconds and 15 seconds is a life and death. And so there are, so all of these sort of closing the loop and the timescales involved, it all become very critical, and they all become heavily interdependent. So how tractable is it as we take this forward into sort of a generic situation?
That's a great question. And my first answer is going to be, we have not tackled that. So by absolutely, this is sort of a fabricated experiment in which we're ignoring a lot of those complexities. One of the things that we thought a lot about, even in this particular example of trying to make it more realistic, was, would there be, let's say that this particular risk case was such that, you weren't just going to get injured, that it really was exactly like a life and death situation. And so that's where I think, in terms of I think there's a non-trivial question here about how to define your control objective. So we also spent a long time thinking about, so we ultimately converge on this idea of just minimizing their time, but giving a user the ability to sort of tune this data where, for example, it might be the case that, yes, you want to do it as fast as possible, but you absolutely can't afford to have the human ever make a wrong decision. And so it's worth, expending that extra time. There could be other lower risk situations where you weight it the other way. And I think that ultimately in any context, and I think there's more research to be done to think about how to define the objective functions. And in fact, so I'm currently a part of a team that has a CPS Frontiers, where we're now looking at how humans interact with automation in learning contexts. And so there, you've got a different type of, even in that type of situation, things can be more or lower risk. And you might start to think about not just what are the objectives from the automation's perspective, but what are the objectives from the human's perspective. And for a particular individual and their own risk propensity, for example, it might be more or less important to do something quickly and or not. And so there's an opportunity there to also maybe use things like inverse reinforcement learning and other mechanisms to try to back out what is the human's cost function. So I think that it is challenging, but that's another piece of it, is that you do have to pose your objective correctly. And the last thing I'll say about that is that it's not as one of the challenges. It might be easier if we wanted to always maximize or minimize one of our cognitive states, but the truth here is that we're actually interested in a calibration. And so there is an optimal value, if you will, of trust and workload and so forth. And so it's important to kind of keep that in mind as well.
Right. Yeah. Fascinating. We could go on and on. There's so much more that I'd like to chat with you about, but I think we have to call this. And thank you so much for coming and giving this talk. And we learned a lot. And I hope that you'll come and visit us again, and we can have even more in-depth discussions. Brian, take it away.
And again, Professor Jain, thank you very much, and welcome back, even though it's virtually.
Yeah, sure.
So, and everybody and all the participants, thank you for joining us today. Please join us next week, same time, same channel, for the next MECI Alliance seminar talk, where we'll hear from Professor George Barbastathis, speaking about physics and machine learning, a match made in adversarial heaven. So again, this is the opportunity with the MECI Alliance to hear from our internal folks, our students, our postdocs, our faculty, and our external, our alumni, industry partners. So please join us next week to hear from George, but also if you would like to recommend some speakers, whether it be yourself, your colleagues, or others, do drop us a line. We'd love to hear from you, and everybody stay safe and have a good remainder of your day. Again, Professor Jain and Dr. Annaswamy, thank you very much for a wonderful discussion today.
All right.
Thank you so much. Thank you, Dr. Annaswamy.
Okay. All right. Bye.
Bye.